Good morning. This is lecture 2 of Unit 3 for AP Chemistry. We are covering all of the sections on gases today. So, a little review of gases and how they are kind of set up. Gases have particles in constant motion. The frequencies of their collisions and the average spacing between those particles depends on the temperature, pressure, and volume of the gas. And gases have no definite volume or shape. I'll add here that gases are also compressible, meaning that they can be pushed or expanded into any different size. When we expand on those ideas in AP chemistry, we call it the kinetic molecular theory. And the kinetic molecular theory has 5 parts. The first is that gases consist of very large numbers of tiny spherical particles that are far apart from one another compared to their size. So we're not thinking so much about the intermolecular forces or the geometries of these molecules. We are picturing their particles basically as point particles because there is so much space inside of a gas. Gas particles are in constant, rapid motion in random directions. Their collisions between the gas particles and between the particles and the container's walls are elastic collisions. And so if you look over here on the right side of the slide, I have a visual for what an elastic versus an inelastic collision is. Inelastic collisions are the collisions that we see every day. This is if you drop a tennis ball, it will bounce, but it won't bounce as high as the height you dropped it from, and it will slowly bounce lower and lower until it eventually stops moving. That's an inelastic collision. In an elastic collision, this tennis ball would not lose energy when it was falling. There would be no gravity weighing it down, there would be no friction weighing it down, and it would just bounce to the same height and not lose energy every single time. Those are the collisions that we assume in our gas law calculations. Even though we know in reality these are not what's happening, the amount of energy lost by a gas particle is so small that we just basically discount it. Number 4, there are no forces of attraction or repulsion between gas particles. We know that this also can't be true. This is chemistry. We've just learned all about intermolecular forces, and we know that there are attraction forces, but since these particles are so much further apart than the forces in or the particles in solids and liquids, we generally just say that those forces don't affect the behavior of the gas. And then number 5 is that the average kinetic energy of gas particles is dependent upon the temperature of the gas. We'll talk a lot about kinetic energy, particle speed, mass, and we'll look at those Maxwell-Boltzmann graph diagrams that we started in class the other day. This slide is a reminder of the gas relationships that you learned in honors chemistry. We learned 3 laws: Boyle's law, Charles's law, and Gay-Lussac's law. You weren't responsible for naming the law along with the relationship, and you're still not, but you are still responsible for these 3 relationships between two variables. In all 3 of these laws, there was a constant amount of gas. Remember, the variable for constant amount of gas, or moles, is N. And in all 3 of these laws, we're working a closed system, so the amount of gas is constant. That's how we do that. So Boyle's law says that pressure and volume are inversely related under constant temperature. We used a couple different demonstrations for this. We put books on top of a syringe, we put marshmallows in a syringe, and pushed and pulled to watch the gas contract and expand the marshmallow. Charles's law says that volume and temperature are directly proportional. That means that as you increase temperature, you can expect the volume of your gas to go up. This only works under constant pressure, which means you have to have a flexible container. The best example of this law is putting a balloon in a freezer and then putting it in a really hot environment and seeing the size of the balloon change. And then Gay-Lussac's law is the relationship between pressure and temperature. Pressure and temperature are also directly proportional. When you increase the temperature of a gas, if you have a constant volume or rigid container, you can expect the pressure of that gas to increase. These are what the graphs of those relationships look like. This is the inverse relationship between pressure and volume. Notice that as you increase volume, pressure goes down. Here's our volume versus temperature and our temperature versus pressure, right? We can also look at what happens when we change the number of moles or change the amount of gas. So if everything else is constant and you increase the amount of gas in a container, then the pressure will go up. This is true in a bike tire or a car tire. Similarly, if you have that flexible container and the pressure is constant and you increase the number of moles, then the volume will go up. This is blowing up a ball or a balloon, right? Pumping gas into a system. This is a Maxwell-Boltzmann molecular speed distribution. This one is for the first 4 noble gases on the periodic table. We can see that we have helium, neon, argon, and xenon all present here. What it's showing here is the probability of particle numbers, right? So this would be the probability density, means how much of the gas is at that speed. And then the x-axis is speed, and this is speed of individual particles. And we could take a couple things from this graph. The reason that the graphs are different shapes is because they are all the same number of particles, so we have to account for every particle. And you can notice that not every particle in a sample of gas has the exact same speed. Our purple line here is for our heaviest gas, xenon, with a mass of 132. That's the molar mass of xenon. And what you notice is that those heavier particles have slower speeds. And I think that's pretty intuitive, that as the particle gets lighter, the average speed of the molecule gets higher. Something to know about this is that this is the relationship between mass and speed. If we look over here at this formula, it says that the average kinetic energy is equal to 1/2 times the mass times the velocity or speed squared. Now, we're not going to do actual calculations with this formula in chemistry, but what we are going to do is look at the relationship between mass, particle speed, and average kinetic energy. These two facts will help you sort of discern what's going on in these graphs. The first one is the most important. It's that 2 gases at the same temperature will have the same average kinetic energy. We have to differentiate here between average kinetic energy and speed, because this graph is for all of the noble gases at constant temperature. So these 4 gases are at the same temperature, but we notice that their masses and particle speeds are varying. Gases with higher molar masses will have molecules with lower average speed. So a heavy gas at 100 degrees Celsius per se will have a slower speed than a light gas with a small mass, also at 100 degrees Celsius. Last year you learned 2 major gas laws to do your calculations with. You learned the ideal gas law, where pressure times volume equals the number of moles times the gas constant times temperature. And you also learned the combined gas law. The combined gas law is for gas that is changing conditions. So you have to have 2 values for at least one of these variables. So you can increase the pressure and predict what happens to either the volume or the temperature. And you may remember that we learned one gas law to combine all of the other gas laws, because if a variable is constant and you're using the combined gas law, you were allowed to take it out. You also could just put in placeholders of 1 for both of these. That's what you're really doing mathematically. But basically, if you have a change in pressure at constant temperature and you want to know about volume, you can take the T out of your equation because it's constant. In the ideal gas law, we use the gas constant, R, and there are a couple of different values. These gas constants are on your AP Chem reference sheet. And remember, you're choosing your gas constant based on your unit of pressure. So if your pressure is in atmospheres, you're going to use 0.082 as your gas constant. If your pressure is in joules, then you're going to use 8.31 as your gas constant. There is a new mole conversion that we're going to learn that tells us that 1 mole of gas is equal to 22.4 liters of gas at STP. So remember, you already learned that 1 mole equals molar mass of any gas using the periodic table. And you already learned that 1 mole is equal to 6.02 times 10 to the 23rd particles of gas. So now let's look at this volume conversion and talk about when to use it and how it can save you a little bit of time.
All right, here's an example of how to use the conversion factor that tells us that at STP, there's 1 mole for every 22.4 liters of gas. The first thing I'm going to do is show you one way that you can solve this that you already know about. So if I read this question, it says, how many moles of CO2 gas are present in 5.67 liters at STP? Remember, STP stands for standard temperature and pressure. So we already know how to solve this problem by using the ideal gas law, PV equals nRT. If we solve it that way, we know that P at STP is 1 atmosphere, that's our standard pressure. The volume is straight from the problem, that's our 5.67 liters. Our R value that we choose is 0.0821 because that's the one that has atmospheres in the unit. Remember, we're matching our pressure unit to the correct R value to choose that value. And then the temperature is standard temperature, which is 273 Kelvin. So our variable or our unknown is N or moles. This question is asking about moles, so we're in good shape. Here's how you would set that problem up, plugging in your values for pressure, volume, N is your variable, R, and temperature. And then to solve for this, I just isolated the variable. I divided 5.67 times 1 by 0.0821 times 273. And I get 0.253 moles equaling N. And you can do it that way. You still get this is the correct answer. But to speed things along, there is another mole conversion value or another mole conversion equivalence where 1 mole equals 22.4 liters of gas as long as that gas is at STP. It does not matter what gas it is because gas particles are so small compared to the space they take up that the mass or the size of the atoms for the gas is not going to matter. This is true. You just have to be careful that you only use this equivalence when you're dealing with a gas. Oops, sorry, let me move my camera over. I'll write it down here. At STP. And so here's what that problem looks like if you use this conversion factor. You still start with your 5.67 liters, but this time you're just doing a mole conversion. So you're multiplying by 1 mole over 22.4 liters. 22.4 liters goes on the bottom so that your units match for your dimensional analysis. Moles is going to be your end unit, and you get the same answer, 0.253 moles.
Okay. Another gas law that is new this year is Dalton's law of partial pressure. This one I think is pretty easy. It just tells us that the total pressure of a mixture of gases is the sum of the partial pressures of each gas. So in this example down here, if we combined a gas with pressure 1 with a gas with pressure 2, then we would add those two pressures to get the total pressure of that gas, of that mixture of gases. Here are some gas law problem tips to keep in mind when you're doing gas law problems. The first is that standard temperature and pressure, which is often written just as STP, is equal to 1 atmosphere and 273 kelvins. You must use Kelvin temperatures in all gas law calculations. If you need to convert from Celsius to Kelvin, remember you take your Celsius temperature and add 273 degrees. If there are initial and final conditions listed for the same gas, you use the combined gas law. If you have 1 mole of any gas at STP, it equals 22.4 liters of volume. You need to match your R value to the units of pressure used in your problem. And the ideal gas law uses moles, not mass. So we want to be very careful when we're looking at mass versus moles. Remember, if you have the mass of a gas in grams, you can use the molar mass to get to moles, and that's what goes into your ideal gas law. Before I move on to talking about a special type of problem, I want to talk about deviations from the ideal gas law. So ideal gases are not real. So things that are true that we sort of eliminate when we're talking about the kinetic molecular theory is that gas particles do have volume, and gas particles can interact with each other through their intermolecular forces. And these properties are most evident at low temperatures. So if gas particles are moving slowly, their collisions are going to be more eventful and impactful. And at high pressures, which is close to the condensation point. So anything that pushes the gas particles closer together is going to increase the effect of gas particle volume and gas particle intermolecular forces. Okay, so for the final part of this video, I want to take you through a problem demonstration that answers the question on this slide. The question on this slide says, what is the density of oxygen gas at 5 atmospheres and 27 degrees Celsius? Let's take a look.
This problem is an example of the type of problem that we are going to get better at throughout the year during AP Chemistry by practicing these skills. So this is a question that you might read at first and realize that it doesn't have an obvious answer. So what you have to do when you see a question like this is practice getting good at taking stock of what you know and seeing how you can connect it to get to the answer that they want. So the first thing that I'm hoping that you will think of is a few of the formulas that you know. So one of the formulas that you know is the density formula. You know that density equals mass divided by volume. You also know the ideal gas law formula, PV equals nRT. And you know the combined gas law, which is P1 V1 over T1 equals P2 V2 over T2. And we know that when we have a gas law problem, we have to choose between them. So let's take a look at whether we should be using ideal or combined for this problem. We want to know the density of oxygen gas, so we know the identity of our gas, and we know the pressure and the temperature. So if I look at the ideal gas law, I can see that I'm missing moles and I'm missing volume, but I do have pressure and temperature, and I know the R value, the gas constant. If I look at the combined gas law, I need 2 sets of values for the combined gas law, even if I have something that's constant that I can eliminate. So for this problem, I only have 1 pressure and I only have 1 temperature. I don't have 2 sets of gas conditions, so I'm not going to be using the ideal gas or the combined gas law. I'm going to try to now make a connection between the density formula and the ideal gas law. The first thing that I did was see how close I could get the ideal gas law to the density formula. The density formula is mass divided by volume. The 2 things that I'm looking for in the ideal gas law that I don't have are moles and volume. So if I rearrange the ideal gas law, what I did here is divide both sides by RT and also divide both sides by V. And what I get there is that N over V equals PRT. And you can see a comparison here between the density formula and the ideal gas law on the left-hand side here, where I have N over V. So I'm comparing now M over V to N over V. So then the next thing that I'm going to take a look at here is the difference between moles and mass. I'm going to move my camera a little bit here. N stands for moles, and M stands for mass. Let's see what I can do here. And one thing that I know is that this is oxygen gas, and I have to remember that oxygen is diatomic, so oxygen is O2 gas. So the connecting factor between moles and mass for me here is that 1 mole of any substance is equal to the molar mass in grams. That's one of our mole conversion facts that we learned. And I know that since I know it's oxygen gas, I can say that 1 mole equals 32 grams for oxygen. So I'm getting there. Now I have to figure out a formula for connecting mass and moles. I know that the moles of oxygen is going to equal the mass of oxygen times 1 mole over 32 grams. So if I solve there for N, my formula for N becomes mass over 32. Now I can plug that N into my ideal gas law that I rearranged. So N over V equals PRT becomes mass over 32 times V equals PRT, equals P over RT. And when I do that, then I can multiply both sides by 32 and find out that the mass over volume is going to be equal to 32 times P over RT. This is good because I was looking for the density, which equals mass over volume. So now this is going to be the density, and it's going to be equal to 32 times the pressure times the gas constant times the temperature. And then I can solve my problem because I have the pressure, the gas constant, and the temperature.
Okay, and that is the end of our second virtual lecture on gases. See you in class.